So on the screen you see a picture from your textbook, if you're in my class, that shows the nature of an electromagnetic wave. An electromagnetic wave is a phenomenon that is produced by accelerating charges. So if you take a charge and you shake it up and down, you get an electromagnetic wave. This is kind of what you saw in Physics 1, where you took a rope and you shook it up and down and you got a wave in the rope, right? If you take a charge and you accelerate it back and forth, like say in a long piece of metal that we call an antenna, you get produced an electromagnetic wave. So what is an electromagnetic wave? Well, primarily the name tells you that it's got an electrical component and it's got a magnetic component. If it's hard to see, the electrical field component is in orange, which I wrote in lavender or something, and the magnetic field component is in blue. Notice what they are. Of course, it's a wave, so we expect these to have some sort of wave nature, which we've given them a sinusoidal nature here. But notice the electric field wave the electric field component of this E&M wave consists of an oscillating electric field. It is constantly changing in magnitude and it changes direction. So all of the machinery you have developed to talk about waves, such as wavelength, frequency, etc., come into play here. You've got a component which is an oscillating electric field, and you've got a component which is an oscillating magnetic field. Notice the magnetic field and the electric field have some things in common. They both have their peaks or their maxima and their minima at the same point in time. When the E field is at a maximum, the B field is at a maximum. When the E field is at zero, the B field is at zero. They are completely in phase in that nature. There is something critically different here, though. Notice the orientation. Because these are vector fields, they have an orientation. The electric field and the B field are always orthogonal. The electric field is always perpendicular to the B field and vice versa. They also have a direction of propagation that's given to you in this little graphic here, which is a little bit out of frame. There is a direction of propagation. Notice that the direction is also orthogonal to both the magnetic field and the electric field at every point. So we can say this. If I make these vectors, this now makes some sense, right? The electric field and the B field are perpendicular to each other. They are mutually perpendicular to the velocity vector, which is, in this case, right along this axis. So this wave is traveling in this direction, consisting of two components, an E field and a B field. Okay, so of course we know that the speed of this electromagnetic wave, we saw this in the last video, is c, which is about, I should say about 2.99 times 10 to the 8th meters per second, 186,000 miles per second if you really like that system, but about 3 times 10 to the 8th meters per second. Really quickly. So what are we going to do with this? Well, there's a couple things we can couple ways to characterize the waves. Number one, I would say that the electric field and the magnetic field components, since by themselves they constitute some sort of sinusoidal nature, can be described independently of each other, even though they are connected. So let me introduce you to these equations. We will say that the electric field, which is a function of space, which I will write like this, and time. Right? It's a function of position, and it's a function of time because it's changing in time, is equal to E naught cosine kx minus omega t. Am I still in frame? I am. Plus phi is the complete version of that. Now, if you remember from Physics 1, when you saw a traveling wave equation, or even when you saw an equation for simple harmonic motion, which also involved a cosine function. What was sitting out in front here was the amplitude. And if this was a mechanical wave, it's actually how high the wave is in space. Or if it's simple harmonic motion, like say a mass on a spring, it was the maximum displacement undergone by the mass. In this case, it's going to be the amplitude, but it's not measured in meters, right? The amplitude is of the electric field, and so E naught is going to be the maximum value of the electric field. It's what it is here at the peaks and also by magnitude at the troughs, right? So we have the amplitude of the wave sitting here in front of us. Let's remind ourselves what these are, or maybe learn them if we've never seen them before. K is the wave number. Let's go with frequency first. That's easier to see. Omega is the angular frequency. So related to the linear frequency by a factor of 2 pi. All right, the linear frequency is how many cycles per second it takes this wave, or this wave is undergoing, how many cycles in every second. The angular frequency is related to that by a factor of 2 pi. Turns out this is easier to use when we're characterizing the wave, so we always typically go with the angular frequency. This is the angular wave number, usually just called the wave number. There's a linear frequency and an angular frequency. There's a linear wave number and an angular wave number. It just turns out that no one ever uses the linear wave number. So we call this the wave number. I don't really like that term though. What this is the amount of waves I can fit into 1 meter. What is the frequency? It's the amount of waves I can fit into 1 second. This is the temporal frequency. If I were to actually see a traveling electromagnetic wave and pull out my meter stick and slap it down, bam, how many, let's say that this is a meter, how many cycles are in that meter? Well, I see 1, 2, so I would have a wave number here of 2. I call it the spatial frequency. It's how many cycles fit inside 1 meter. This, of course, is the linear wave number, K, which is related to lambda, the wavelength, by another factor of 2 pi. So if you have omega or if you have K, you have the linear frequency and you have the wavelength. Of course, the frequency, remember, is 1 over the period being, not tau, t, the period being how many seconds it takes to complete 1 cycle. And we furthermore have at our disposal the wave speed equation, which in general says that the speed of a wave is equal to its frequency times its wavelength. In our case, because these are electromagnetic waves, we know what the speed is. So C is equal to F lambda for any electromagnetic wave that is traveling in vacuum. We're going to see in the next chapter that the speed of light can slow down if you're not traveling in vacuum. But for this case, we're going to imagine we're traveling in vacuum or air, and the speed of the wave is C equal to F lambda. So that is how you pick out, or that is how you read this equation, and is how, which is of the electric field component. And these tell you how to relate what you see here to frequencies, or to terminology that you already know. Really, if you're given an equation of this form, you can just read off the values. I'll show you some examples in a second. You can just read off the values and use these simple equations to get to what you need. Of course, there is another component to this field, the electric field. Sorry, the magnetic field. I gave you the electric field. Magnetic field will be characterized basically the same. It is also a function of space and time. It will be equal to B naught cosine kx minus omega t plus phi, where B naught is now my amplitude of the magnetic field portion, my wave number, my angular frequency and my phase angle are exactly the same as they were for the E portion of the wave. But they have to be because they are coupled. I forgot to talk about phi. Phi is the phase angle. This basically enables you to start your stopwatch anywhere without having to set it equal to 0. In other words, if you're starting out at x is equal to 0, or maybe all dimensions are equal to 0, you're at your origin, and you're starting your stopwatch when this wave is at the origin, then you get 0, 0, and you get cosine of 0, which is 1, right? Which would get you B naught, the maximum field here. But as I've drawn it, that's not the maximum, that's the minimum, if I can show you, right? This is 0. So in that case, maybe cosine was the wrong choice. You should have chosen sine. All right, that's really obnoxious to have to do. To get around that, we add in the phase angle to say that, you know what, if it doesn't line up exactly with the cosine function, I can always shift it. This represents a shift. Remember that the difference between sine and cosine is just a shift or a phase angle. So don't let this bother you very often. This one is 0. The important thing here is the wave number and the angular frequency and the amplitude. All right, so what can we do with that? Well, just as an example, if you were to see an equation of this nature, E of x and t is equal to 1500 volts per meter times 450 inverse meters, or 450 per meter, x minus omega t. Now we're say, all right, well, what is the peak value of this wave? What is the maximum E value? I mean, it's sitting right here in front of it. You just read off. You compare it to the equations I just showed you, and it's just that simple. E naught is equal to 1500 volts per meter. All right, no big deal. Well, what's the wavelength of this? Well, right in front of you, I have the wave number, 450 per meter, which are the units of the wave number. Remember, it's cycles per meter, just like frequency is cycles per second. Can I then find the wavelength? Yes, I have this expression at my disposal. 2 pi over lambda. So let all that equal to 450 per meter. It looks like lambda then is equal to 2 pi times divided by 450 meters to the inverse meters. Of course, this is an inverse in my denominator. It will flip up to the numerator. Forgot to pull up my calculator. Let me do that. Looks like I get that my wavelength is about 13.96 millimeters. Somewhere about there. I got 0.01396, so it's about 13.96 millimeters. I just read it off there and then applied this simple equation, right? Make sure I did the algebra correctly. Yep. All right, so now what is the frequency? Well, I don't have an angular frequency here that's been given, but I do know that C is equal to F lambda. Therefore, F is equal to C over lambda. So what do I get? 2.99 times 10 to the 8th meters per second divided by 0.01396 meters. Have to make sure I match up the meters. Let me run this. I get about 2.14 times 10 to the 10th. Okay, and really, it's that simple. This is basically how you handle equations of this nature. Now, there's one other way to relate these two. Well, there's several other ways to relate these waves, the electric and magnetic field portions of this wave. Let me show you a very important one. Turns out that if you take the E field at some time and the B field at the other time, or sorry, at the same time, and you form this expression, what you always get is the speed of light. I should say always, except when the B field is 0, of course, which it is every now and then. But this is a really interesting way to relate the electric and magnetic portions of an electromagnetic wave. Of course, if this is true at any time, it has to be true at the peak times. So the more useful way to write this is E naught over B naught. This is true at every point, but if you're given then the maximum electric field, this equation allows you to get the maximum B field almost without thinking about it, and vice versa, right? In the next video, we're going to see a few more equations that we're going to use to relate these two, as well as to determine the direction of propagation.